Good morning, everyone. Can you give me 1 second to share my screen? Good morning, everyone, again, and hopefully you can see my screen. Thank you so much for joining us today. It's actually the first webinar in the PoDIUM's Living Lab series, and today we will be exploring the Spanish Living Lab and its use cases, focusing on the projects and challenges to date, and highlighting all the innovative work, of course, that has been done from our Spanish partners and within the PoDIUM project. My name is Seve Christoforou, and I am a Communications and Dissemination Officer at ICCS, the Institute of Communication and Computer Systems in Athens, Greece, which also the organization coordinates the PoDIUM project. I will be moderating the webinar for today, so before we begin, I would just like to remind you that you can always submit your questions at any time using the Q&A option on your control panel. However, we will be addressing all questions together at the end of the session. We will be reserving 10 to 15 minutes to answer to all your questions then. To kick off, I would like to introduce our speakers and invite them all to turn on their camera so we can see you.
Good morning, everyone.
Super, thank you so much. So we are delighted to welcome Yorgos Zacharopoulos. He's PoDIUM's day-to-day manager and my dear colleague from ICCS, who will be providing a high-level overview of the Spanish Living Lab, of the project and the Spanish Living Lab. Then we have Jorge Suarez-Luque from ETRA IND, who will be delving into the use case that focus on PDI for a user-centric CCAM-enabled traffic management in urban corridors with high priority vehicles and vulnerable road users. Oh, there's been a change. And then we have Charilaos Vasiliadis. He's an innovation and strategy consultant at Autopistas, and he will be presenting the use case that focus on real-time responsive PDI for CCAM-enabled traffic management in the Mediterranean cross-border corridor this time. Hi, Charilaos. And then finally, last but not least, we have Yasin Castells from IDIADA, who will be highlighting the role of 5G and CV2X connectivity in the Spanish Living Lab. Thank you all for being here. I'm looking forward to seeing your presentations. And without further ado, without taking any more of your time, Yorgos, would you like to give us an overview of the Spanish Living Lab?
Yes, absolutely. Just give me 1 second to set up everything and start sharing my screen. So, sharing screen. I hope you can see that.
Yes, if you can put it on presentation mode also.
Yes. I think now it must be in presentation mode.
Super.
I think we are good to go. Right. Can you hear me? Yes. Yes.
Yes. See you, hear
cool.
you.
Great. Right. So, good morning or good afternoon, everyone, depending on where you are based. Thank you very much for joining this webinar for the PoDIUM Spanish Living Lab. My name is Yorgos Zacharopoulos. I'm the day-to-day manager, project coordinator for PoDIUM, and I'm also a project manager for ICCS, as Sevi described earlier. I thought it would be better to give you a few details about PoDIUM in general before introducing you to the Spanish Living Lab. So PoDIUM is derived from physical and digital infrastructure, PDI, connectivity and cooperation enablers, building trust and sustainability for CCAM. So we are building urban and highway use cases on the facilities of 3 well-equipped living labs. one in Germany, one in Italy, and last but not least, the one that we will discuss about today, the one in Spain. In total, we have 26 partners from 8 countries, a budget of 12 million euros, and a duration of 36 months starting in September 2022. And we're looking to complete the project in the upcoming September of 2025. We're developing 5 use cases, of which 2 are developed in Spain. And the purpose is to tackle all the different requirements for the availability and performance of connectivity, as well as the different cooperation enablers per use case. Oh, sorry, wrong slide. PoDIUM aims to support the 5 advanced use cases of connected and cooperative automated mobility in actual real traffic conditions. The 5 use cases are looking to advance in a set of key technologies, both in the physical and digital parts of the infrastructure, in order to achieve the following list of bullet points that you can see there, which is firstly creating a multi-connectivity approach to ensure reliability, availability, and of course redundancy of the PDI system. Secondly, to advance in data fusion and integration of multi-access edge computing to the proposed hybrid data management environment, so we can enable enhanced environment perception models towards digital twins. Also, we are looking to extend the CITS messages for enabling advanced CCAM use cases. Also ensure software integrity, trust, and truthfulness of the CCAM data and their exchange patterns and their processing methods. And finally, demonstrate urban and highway use cases in a diverse set of configurations, with the integration, of course, of vulnerable road users or VR users. You will probably see them today been mentioned. Oh, sorry, slides are going a little bit faster than I wanted. There, okay, great. So the PoDIUM architecture. The architecture consists of 3 layers that you can see on the left-hand side, all interact between them. The first is the road level system, the second is the edge layer, and the last one is the cloud layer. The road level system includes the data producers, let's say, such as the vehicles, either CAVs or CVs, meaning connected autonomous vehicles or connected vehicles, the roadside units or RSUs, the connected, usually through a mobile app, vulnerable road users, and the sensor processing units or SPUs, which are responsible for providing information related to, let's say, legacy or typical vehicles and other non-connected road users. These are offering communication and computation, let's say, capabilities on the road level, and through the different platforms, through the different platform services on the edge or cloud level that are needed to implement the different use cases. We as PoDIUM classify the communication technologies between the different parts of the architecture as either direct, meaning wired or cellular, hybrid, meaning on an ad hoc basis, or through multi-connectivity. And to ensure the integrity of the software and exchange the CCAM data, we have developed a trusted computing approach on trusted platform modules, or TPMs. We consider this architecture as a general blueprint of the concepts that we have developed in PoDIUM as part of the 3 living labs and the 5 use cases. So as a result, none of the use cases will provide all services and communication technologies, but each one of them will implement a subset of these technologies. Right, and here's a good breakdown of what we just described. So one example is the single connectivity communication, such as the 5G wireless connection between the vulnerable road users and the cellular 5G centimeter wave network. And another example is the multi-connectivity that we mentioned earlier, such as the one of the connected autonomous vehicle through various technologies like the 60 gigahertz Wi-Fi, the ITS-G5, or the V2X, as you'll see later, the 5G millimeter wave and the 5G centimeter wave, similar to the VRU. So the multi-connectivity option offers us the ability, firstly, to use multiple communication technologies at the same time. Secondly, schedule messages and data packets over the available communication technology. Then also to ensure the reliability, availability, and redundancy. We are insisting on that, it's very important. And also, you will hear about that later as well, about the reduction of latency, which is also very important. And going to the living labs, as we mentioned earlier, through our 3 living labs, we have 5 use cases being developed. And across all 3 living labs, there are some common PDI aspects being used, such as the multi-access edge computing, or MEC, as you might see it later, the 5G coverage or 4G coverage, depending on the area, the RSUs, roadside units, the connected automated vehicles, and the mobile devices playing the role of the vulnerable road users. A few details now about the other 2 living labs before we start discussing about the Spanish one. At the German living lab, we have one use case 1, that focuses on the benefits of a cooperative local environment model for managing complex urban traffic situations. And please join us also at the German Living Lab webinar on the 3rd of December to hear more details about that. Now at the Italian Living Lab, we have 2 use cases, use case 4 and use case 5. The first one, use case 4, focuses on an infrastructure-based application for safe and efficient traffic management at urban intersections. Actually, that will take place in Turin. Which assists connected automated vehicles at the crossroads and protects vulnerable road users. The second one, use case 5, focuses on the issues related to tunnels. So tunnels have safety critical risks that always need to be taken into consideration. And at the same time, tunnels face technical issues related to cooperative ITS because of the absence of open sky conditions needed for any ordinary GNSS services, meaning related to common time and space reference for the vehicles. So this high-risk use case addresses both issues with one service, which monitors traffic, assesses risk, and assists vehicles before and within the tunnel through CITS, despite the absence of time and space reference, let's say. And lastly, about the Spanish Living Lab. So the Spanish Living Lab plays a crucial role to the development of PoDIUM. Our Spanish partners, which include both academic and industrial bodies, are offering their great experience and expertise, especially in the development of the 2 use cases that you will hear about right after me. But just very briefly to describe you what those 2 use cases are aiming for. So use case 2 aims to enhance urban control traffic by sharing with the infrastructure the information that can be provided by connected vehicles. It is composed of 3 different scenarios that address different situations that will take place at the same time in a corridor in the city of Barcelona. The first scenario is focused on the management of high priority vehicles. In this case, you will see later from Jorge, it's a firefighter truck, which will need to indicate its route to the traffic management system, asking for priority at signalized crossings and setting its location at all times. While on the other hand, the infrastructure will send back warnings to the rest of road users that an emergency vehicle is approaching. The second scenario aims to optimize traffic management strategies by using information provided by connected vehicles. And as a result, all connected vehicles on the road will be sharing their speed, location, origin, destination, etc. with the traffic management system. And at the same time, the infrastructure will provide all the connected vehicles with information on the traffic status and route options while selecting the best traffic control strategy. And lastly, about use case 2, sorry, in the third scenario, which is the vulnerable road users protection, the infrastructure detects the presence of VRUs and evaluates the potential risks. So if a VRU is in a risky situation, the infrastructure sends warnings to the connected VRU, and at the same time it sends warnings also to the vehicles about the presence of the VRU. And just right after me, you will hear more details about that from Jorge. And lastly, from my side, use case 3 is exploring 2 cross-border scenarios related to daily commuting and safety incidents. We are introducing a new system that enables vehicles and road users to cooperate with the road operator and implement real-time traffic strategies for safe and smooth traffic. Now, the PDI system will incorporate internal and external data to generate traffic status perception for each section of the road at the cross-border area. And the system will calculate potential scenarios and traffic management strategies. And in the event of an incident, the PDI will respond quickly by communicating with incoming vehicles and the vehicle involved in the incident. And that is all really from me. And now we'll pass to Jorge, who's going to present more details on use case 2. And thank you very much.
Hello, Yorgos and everyone. Well, I'm going to share my screen first. Can you see it, right? Okay.
Yes.
Okay, thank you. So, well, since ETRA is the leader of the use case 2, this part of the Spanish Living Lab, so I'm going to present the main aspects of this use case, describing what we are going to demonstrate on it and focusing on the progress made and the main challenges that we are facing. As mentioned in the use case title, the aim is to demonstrate the support of the physical and digital infrastructure for CCAM-enabled traffic management in urban corridors involving high priority vehicles and vulnerable road users. This is the content I'm proposing. First, an overview of the use case, followed by a detailed description of the 3 scenarios that will be tested and have been presented by Yorgos. After that, I will go into detail and show some services of the PoDIUM platform that are related to these scenarios and how we will integrate them with the traffic management system. Finally, some aspects of the vehicles that will be used to test the described scenarios. So the test site is in the city of Barcelona, as Yorgos mentioned. It's in a complex urban area along a major avenue with more than 50,000 vehicles per day. Along this avenue, a firefighters corridor of 3 kilometers has been defined, crossing a series of intersections controlled by traffic lights and a large number of pedestrians and bicycle lanes. Sorry. At the end of this corridor, we have defined an area consisted of a group of streets and intersections which will be used to test the traffic management optimization scenario. And finally, a particular crossing of this area has been selected to test the BRU protection scenario. It's due to its specific characteristics as it has some bicycle and pedestrian lanes crossing the avenue, which could lead to a risk of collision between them. Let's go into detail on the description of each scenario to be tested, starting with the priority to emergency vehicles. In this scenario, we are going to test 3 different functionalities with the support of the physical and digital infrastructure, the assignment of the emergency corridor at the fire station, the green priority to the emergency vehicle along the corridor, and the maneuver of the connected and automated vehicle to give way to the emergency vehicle. So in this slide, we saw the sequence of actions defined at the fire station in the event of an emergency. First, a specific corridor is assigned depending on the location of the emergency that has to be attended. Then a specific vehicle is assigned and detected by infrared when it leaves the fire station. And finally, the traffic light priority is given to the emergency vehicle at the first intersection. Here we have a little animation. We open the green light so the vehicle can move along the corridor. So these actions are managed by 2 types of messages received by a new service. It's the emergency priority manager. It's connected to the traffic management system. So one message is sent by the emergency system, contains information about the corridor assignment and the vehicle that is leaving the fire station. And a second message will be sent by the emergency vehicle, transmitting its position every second. Regarding the second functionality, the traffic light priority for the emergency vehicle, which is shown in this slide, the emergency priority manager uses the position sent periodically by the emergency vehicle to make a prediction of the arrival time at intersections along the corridor that are equipped with traffic lights. Then it asks the traffic management system at the appropriate time to send the priority requests to the traffic controllers so that the emergency vehicle can pass through the intersections with green lights. Here a little animation showing this scenario. We open the green and the vehicles pass through the intersection. Well, at the same time, the traffic management system optimizes the phases of the traffic lights at intersections to reduce the waiting time for the other vehicles, and then optimizing the overall traffic flow, both at the intersections and along the corridor. Well, finally, in the third functionality in this scenario, it's the cooperative maneuver carried out by the vehicles. The vehicles will send their position to a new service. It is the cooperative maneuver recommender. At the same time, the emergency vehicle also sends its position to this service, which estimates the coincidence of both vehicles, and whenever suitable, it sends messages to the vehicles recommending them to leave the reserved lane for the emergency vehicle. So the connected vehicle receives the message through the HMI. This is developed by IDIADA, which is shown in the picture on the right, and showing the speed of the vehicle and the distance between it and the emergency vehicle, which is approaching to the vehicle. Well, then the driver reacts correctly. And in the case of an autonomous vehicle, which is developed by Mila, it receives the same message, but it reacts autonomously. And what here we have some challenges, key challenges that we are facing in this scenario. Well, in order to reduce the time to reach the emergency, we need to improve the circulation of the emergency vehicle along the corridors with short green phases and adjusted to the vehicle that is passing the intersection. There is also a system that is currently deployed in Barcelona to predict the arrival times of the emergency vehicle at intersections. It is based on beacons detecting the presence of the emergency vehicle at the intersections, but it's not working so properly. So we intend to improve this system by using this new function. And we also need to optimize the current traffic flows even on crossing streets along the corridor. So let's move to the second scenario, the advanced traffic management based on real-time response. That begins with when all connected and automated vehicles on the road send their position, the speed, origin, and destination to the traffic management system, which selects the optimal control strategy to avoid congestion and other incidents. To do this, the TMS will send messages to the vehicles about the traffic conditions and hazards so that they can decide on the most appropriate route. Here a short animation, there is an alert, and so the vehicle reacts with an alternative route. The connected vehicles will recalculate the routes based on the information received through the HMI, but the automated vehicles will recalculate the routes autonomously. And some key challenges that we face in this scenario. Well, a new function of the TMS receives and processes the messages sent by the vehicles and generates some traffic metrics. I'm talking about the origin and destination matrices, the travel times and distances and delays and so on. So it needs a certain amount of data from vehicles to process them and obtain, let's say, accurate results to optimize traffic in the area. And on the other hand, the TMS, this service acts as a client of the TMS and receives from it the notification of relevant incidents on the road. So it must therefore rely on the incident information provided by the TMS. Now, yes, to the third scenario, it's protecting about vulnerable road users. Here we selected an intersection with where 2 AI cameras are installed on lamp posts to detect road users, vehicles, and vulnerable road users. And we developed a new function called the collision risk estimator. It's based on the detection of road users, their position and trajectory by using artificial intelligence. We estimate the risk of collision between the vehicles and VRUs and will send them warnings. The connected vehicles will receive the messages through the HMIs, shown in the slide, warning them of a risk of collision with a VRU, and the driver must react by braking the vehicle. This HMI shows the speed of the vehicle and the collision risk warning, and also the automated vehicle, which can see the VRU because there is an obstacle on the road or at the roadside, receives the message and must slow down autonomously. Well, some key challenges in this scenario. Well, the intersection is complex with many VRUs passing the intersection, so we have to deal with a lot of road users. Also, the presence of obstacles can make it difficult to detect the VRUs, so it's important to consider how we are going to install the cameras with the orientation, the angle of view, and so on. The system has to be sensitive to detect quick reactions of the VRUs, depending on their type. But also the system should also eliminate or avoid false positives. For example, road users who are obeying the rules on the roads, so there is no risk of collision. Well, in this slide on the left, there is a view on the camera installed on the street, which also shows the different polygons that could be defined to detect the different road users. This is an example. And on the other hand, on the right side, there are two figures showing the VRU app that we have developed to warn VRUs about our risk of collision. The left one is shows without any collision risk, and on the right side we show the warning when there is a collision risk. Well, now let's move to the functional architecture that is shown in this slide, sorry, but it's particularized to use case 2. It shows the interactions between functions and at different levels. There are 3 large blocks integrating this functional architecture: the platform functions, which includes all the functions that are deployed in the cloud or in the edge, and the external systems that will be integrated, the traffic management systems and the emergency management systems. We have also 2 other blocks, the road users and the sensors and actors. Well, regarding the main platforms functions, these are the traffic management and cooperative maneuver planning, that includes traffic management functions at a strategic level, the digital twin for creating a digital representation of the road network, the risk management function that estimates the risks regarding the collision between different road users, and the CITS message and user handling, which is the main function to provide connectivity to road users. Here we have the road users with the connected and emergency vehicle functions and the connected and automated vehicle functions, but also the VRU ones. Finally, the traffic controllers and the cameras for detecting the road users. Well, and finally, here we saw some pictures of the vehicles that are being prepared for the tests. On the left side, the connected vehicle that is being developed by IDIADA, together with the HMIs for the 3 scenarios. And on the right side, the connected and automated vehicle that is developed by Mila. It's equipped with different types of sensors, you see, and well, they are developing all the autonomous driving functions to prepare the vehicle to react autonomously in all these scenarios explained. And well, that's all. Only I wanted to do a final remark about the progress of the use case in the next months. So we have planned to begin tests by February 2025, and they will be finished by May, June, with a final demonstration where we will evaluate results and the public acceptance. We will also generate a video that will be disseminated at the end of the project, so that you can be informed about the results of this use case. And that's all from my side. I now move to give the floor to Harry, that he's going to present the use case 3.
Thank you very much, Jorge. Hello to everyone. Good morning. I hope you can hear me fine. In the meantime, I share also my screen. So the third use case of the PoDIUM project is about basically connected highways. So we call it a real-time responsive PDI for CCAM-enabled traffic management in cross-border corridors. We're working on this together with my colleague David Porcuna from Autopistas, who was not able to join us in presenting the use case. He's the innovation manager at Autopistas, and we are 9 use case partners in total, including Telnex Retevision, Enidet, Enalac, IDIADA, that is also in this webinar, EDOSCAT, UPC, Mila, and ISFM. So I will talk to you a brief summary on the use case tree, as well as our two scenarios. We're gonna drill down into cross-border connectivity, the platform services that we develop specifically for our use case. What is the traffic management center and the key challenges, and the CITS messages and gateways, as well as the Mila CAV shuttle and our 2025 plans in terms of the final demonstration and dissemination of the use case. So the Spanish side, the use case tree's aim is to ensure a smooth and safe traffic management while enabling interoperability and validating our new functionalities of the platform by leveraging and merging data from connected and automated vehicles, traffic cameras, and third-party providers. Okay, so we have two scenarios. Daily commuting across borders is one of the two. And the second one is the safety incidents across borders, offering a continuous, efficient, and resilient service. Okay. So one is more focused on evaluating the on-demand CAV shuttle service across borders, and the other one to evaluate risks on the new CCAM services, especially safety risks. So scenario one, this is going to be demonstrated along the cross-border highway between Spain and France. The towns of Le Boulou and La Junquera are the points of origin and destination. And the key challenges here were basically how to make the CAV run at 80 kilometers per hour in full automated driving mode at SI level 4. SI level 4 is a quite high automation level for the ones that who do not know. So there is vehicles right now running on SI 4, and let alone there are no vehicles authorized in public roads, commercial vehicles in SI 4. That's why we're doing a private, well-authorized demonstration. And then how to enable the on-demand service by having variable departure times scheduled depending on the passenger demand. Okay, so that's why we have an on-demand service that we will demonstrate. And the idea is how to connect the two sides with of the border with this service. Okay, it's a new business case. The vehicle specifically for this, for both use cases, but specifically for this one, is the Mila CAV shuttle. CAV means connected and automated vehicle. So it's a 100% electric shuttle with 12 passengers capacity. It's an autonomous vehicle, can reach L4 SI level, as we said. It can go faster in manual mode, of course, but right now it's capable to go to safely to 50 kilometers per hour, and by the time of the testing next year, is going to be able to go to 80 kilometers per hour in full automated driven mode. And it's authorized already for routes in France, and we're asking for the permits as well for the demonstrations in Spain. The whole safety is ensured by the telesupervision system of Mila. It's an add-on safety system. Plus, we have, of course, a trained safety driver for the tests. The on-demand service is being enabled by the new on-demand service app for Android smartphones for now. And by next year, we will also be able to have it. And if you come to the demonstration, you can see how it works. So scenario 2 is about the safety incidents across borders. Okay, so we are testing 3 main sub-scenarios, let's say safety-related sub-scenarios. The first one is an incident, for example, a stopped vehicle ahead on the road, which is flagged as a hazard. Okay, that leads to a blocked lane on the road, quite a typical scenario on the highway. So this would require alerting the connected vehicles ahead of time, as well as taking preemptive safety measures by the platform in terms of traffic strategies to be implemented for the vehicles that are approaching there. Okay, so in that case, we will, for example, have the CAV shuttle to slow down, perhaps handle a maneuver to change lane and handle a maneuver around the stopped vehicle, and this will be supported by telesupervision. The same behavior will be taken by connected vehicles which are not automated, but the drivers will have to receive the messages and act accordingly, basically. Safety-related issues. The second is about safety-related issues that are self-reported by the shuttle itself during its journey. In this case, the shuttle says, hi, I have a technical problem. I need to make an emergency slowdown and stop. So it will emit a message to the platform, and the platform will mark it as a hazard, and the message will also be received by other connected vehicles along the way. So the approaching vehicles will have been notified, and the traffic strategies will manage the traffic in more or less the same way that we discussed in the sub-scenario 1. Okay, and the third one is the VRU safety. It's a bit similar to what you heard in use case 2. So we're having a risk collision alert between when we notice that there is a risky situation between VRU and connected vehicles. Okay, so our implementation is there's a smartphone app, and the whole idea was how to be able to send V2X messages from the smartphone and receive V2X messages from the smartphone directly of the pedestrian. Okay, and this is not a technology that pre-exists, so it had to be built from scratch. Scenario 2, going into more detail, will be demonstrated in the Autopistas Future Road Lab, which is close to Barcelona in the Castelldefels C32 highway. And right there we have 3 lanes from each direction. We have 12 CCTV cameras, like traffic cameras, of which of them 2 are implemented with video analytics. We have, of course, 5G network provided by MasOrange, and we have 4 roadside units, which are complementary connectivity via Wi-Fi. In the cross-border connectivity aspects, okay, the whole system works like this. A connected highway comprises of, we have the traffic cameras, of course, this is already quite standard in current highways, on the roadside, as well as we have the RSUs, which provide the CV2X, as we call it, connectivity. Then on top of that, we have the 5G connectivity with the 3G nodes. And on the edge side, we have edge servers, basically, what Yorgos discussed before. We call them an MEC, a multi-edge computing, and the cloud computing. Okay, all of these are connected, as you can see. So, from example, from Spanish side, the 5G and the RSUs are sending data to the edge cloud, and the edge cloud intercommunicates with the cloud computing. Now, the challenge when you have a cross-border are 2. First of all, there is no communication, like the 2 sides of the border are blind to each other. So what we implemented is an exchange of traffic, important traffic and incident data from one side of the border to the other. But this only happens on the cloud level, okay? So if there is an incident on this side of the road and the vehicle is coming on this side, with this exchange of data, the one cloud can let the other cloud know, so it can notify the traffic strategies on before they cross the border. Okay, and the second challenge is that when roaming from one country to the other, you have 5G disconnection, as you know, because you lose the one network and you have to register on the new country network. So this cutoff, we are covering it with CV2X RSUs exactly on the border, which provide this multi-connectivity approach. So when we are losing connectivity with 5G, we are still connected with the RSUs. In terms of how the platform works, just a very high-level idea. We have, again, as you saw before, the connected and automated vehicles and the VRUs. So from one side, the road users. Then you have the traffic cameras, the roadside sensors. And all of these are sending and receiving, in the case of vehicles, data to the platform, okay? And the platform has 4 services, basically. The central service is the traffic management, and the others are the CITS message handling, which sends and receives messages to the connected users. The digital twin, which is basically collecting all the information of the highway, of the users along the highway, and the risk management, okay? And these intercommunicate with each other to actually develop all the traffic management and risk management strategies and messages that you need to send. In terms of the traffic strategies, we have 3 main traffic strategies that we work on the highway. The first one is to reduce the maximum speed limit, okay? When there is a congestion ahead, or when there is high flow of traffic, when there is a rain, when there is an accident ahead or whatever, you go from, I don't know, 100 kilometers per hour, a reduction to 80. Everybody has seen these dynamic speed limits. This we will implement it though via connected vehicles messages. We will not implement it in the real traffic message panels. Increase recommended safety distance from vehicle in front to X. This is a recommendation. Instead of saying, okay, you need to leave 20 meters from vehicle in front, you increase it to 50 or to 100 meters from vehicle in front. And to avoid X lane, the right lane or the center lane or the left lane, depending on which lane is blocked because of an incident, okay? And then the fourth thing that the platform is able to send is alerts. So they send a location and an incident type. For example, there is a stopped vehicle on this location, or there is a congestion ahead in X kilometers, etc. So these are the 4 types, and the traffic strategies are triggered based on the hazards that are received by the TMC, and they're analyzed, and the state of the traffic. So the TMC is like a smart brain, that the traffic management center is a smart brain that is analyzing and developing traffic strategies dynamically. And the input data and sources used are index historic data, enhanced with live traffic camera data, and real-time connected vehicle data. So the newest addition to our TMC is actually the connected vehicle data. And this was one of the key challenges.
Harry,
yes?
May I ask you to wrap up if you can?
Sure.
Thank you.
We have just 2 more slides. So the key challenges were how to collect the connected vehicle data into the TMC. This was a new implementation in our project. How to process the connected vehicle data to generate these strategies. So how to do the data fusion, as we call it. How to recognize hazards, such as stopped vehicles, in the pool of connected vehicle data that we have in the digital twin, and how to contemplate incident alerts that are self-emitted by a vehicle, and then and they need to make an emergency stop. So all of these are being addressed and are going to be demonstrated in especially scenario 2. So as we said, these are the 2 scenarios. In one scenario, mostly working with a Mila CAV vehicle on the on-demand shuttle service, and the second one, where we'll have 4 vehicles. The Mila shuttle, plus 3 connected vehicles, 1 from IDIADA and 2 provided by Autopistas. And the final dissemination will be by September 2025 with the final video and assessment report to be published. And we would be happy for you to receive it. Thank you very much, and I'm happy to answer any questions.
Okay, should I present my part then?
The next one is Justine from IDIADA. Yeah, please.
Let's go. Okay, I'll try to be quick then. I think time is rushing. Well, this is Justine Gasset from IDIADA. I hope you can see my face and also my screen. This is deep knowledge and insights of how use case 2 and use case 3 work with P2X communications. And this is more or less the wrap-up thing that we have. If you remember, we have 3 main use cases or scenarios in use case 2, the priority for emergency vehicles, the traffic optimization, and also the protection of BRUs. All of them are going to be provided by 5G communications, but the protection of BRUs is using also CV2X, because we want to test how the low latency of this technology will bring some benefits. And for use case 3, scenario 2 in particular, in which we have these 3 main recommendations or incident alerts, which is the reduced maximum speed, the increased recommended safety distance from vehicle in front, and avoiding a specific lane. We have 5G as well, and also CV2X. And this is basically a hybrid communication approach in which we want to make sure that the vehicles, regardless of the connectivity that they have, one or another, they will keep receiving and providing information and enjoying the services and the incident recommendations to be transferred accordingly to the vehicles down in the street in this cross-border situation between different countries. And the last, let's say, but not least, scenario that we have in use case 3 is the protection of BRUs at bus stops, which will be offered by 5G only. So one by one and quickly, the emergency vehicle priority scenario that Jorge presented, we will send TAM messages once per second from the vehicles, from the emergency vehicles, but also for the connected vehicles and also the connected and automated vehicle. With this CAM information, the vehicles just send location, speed, heading, and other dynamics information. All of this is used for the TMC from ETRA, from the traffic management, to open the traffic lights, to also generate the DNM, which is the message that comes down to the vehicles from this traffic management, that in this case indicates that there is a lane reserved for that emergency vehicle that is driving and approaching. So this DNM will be handled by the connected vehicles drivers. So they will in the HMI see how this vehicle approaches and they will take the appropriate actions. But specifically, it will handled by the autonomous vehicle. So the autonomous vehicle will change lane and give way to this autonomous vehicle, to this emergency vehicle, time in advance. So it will be a free lane for this emergency. If we go to the next one, the traffic optimization. If you remember, there is also CAM messages sent by all connected and automated vehicles, including origin and destination paths. So the intentions of the route that they have. And as well as with other information, the traffic management will get all this information sent by 5G to analyze the traffic and detect issues. And once an issue is detected, like a congestion, then it will be sent by this traffic management down to the vehicles to alert them about this situation. And we want specifically the autonomous vehicle to take action and to change the route, since their intended initial route will face this problem that the TMC has detected. And for the protection of BRUs, we have both technologies at the same time. With 5G, the BRUs, in this case pedestrians and cyclists, will receive the DNM messages that will be generated by the edge computing service risk analysis, basically, that will, through cameras, will analyze and will detect possible collision risks between the vehicles and those BRUs. And the same alert will be transmitted to the connected and automated vehicles and also to the connected vehicles through CV2X. So both technologies will run at the same time, but for different user types. So we can also compare the efficiency of those. Then for use case 3 speed limit recommendation, we will also have CAM messages. I'm not going to explain it again. The same approach. All the location speed information sent to TMC, but also we have CPMs, which basically means that for those vehicles that will have perception, which have cameras and lidars and radars, so more advanced vehicles, all of these detections that the cameras and the sensors will do in the vehicle, they will be transmitted to the TMC. So TMC can see what the vehicle sees at the same time. Not also because of the CAM messages, but also for the CPM messages. So with all this information, the TMC, in this case Autopistas, will be able to detect the issues on the road. An issue that could also be reported automatically by the autonomous vehicle if it has a problem itself. So when this happens, we will force a situation like this. The autonomous vehicle will report that he has an issue. So both options are there. The TMC gets information from the vehicles, CAM, CPMs, but also the cameras installed in the highway. So detects in order to detect issues, but also the dynamics from the vehicles themselves could report those issues. And once these issues are detected, we have, in this case, the speed limit recommendation, which will be transmitted through IVI messages with that specific speed that is wanted for the vehicles to follow. Together with the mapping messages, which is basically a layout of the highway in order to understand in which area specifically and road segments this speed limit is applying. For the recommendation of the distance vehicle in front, we have exactly the same approach. Once if there's a detection of an event or a possible issue through CAMs, CPMs, dynamics, and cameras, then an MCM message is sent to alert the vehicles to take action and to please keep a minimum distance with the vehicles in front. So the safety issues are minimized together with the MAPM for the same reasons, just to share layout information. And then for the avoiding lane, even though it's a right, center, or right lane, exactly the same approach. We also use the MCM to transmit this avoid lane recommendation. So the vehicles, and specifically the autonomous vehicle, will change lane if it is actually driving on that, let's say, dangerous lane where the events are detected by the other messages. And finally, we have in certain stops that the the autonomous vehicle will do, since there is also the presence of pedestrians there wanting to jump into the vehicle, into the autonomous vehicle or the shuttle to go from place A to place B. We will have those CAMs sent by the autonomous vehicle and the connected vehicles around. We have the VAM messages sent by those pedestrians as well. These VAM messages exactly share the same information as the CAM messages, but for the PoDIUMs, so location, heading, intentions. And then a denim in case there is a risk of a dangerous, say, collision risk between the connected and automated vehicle and those pedestrians is detected. This denim will be sent to both the autonomous vehicle and also the pedestrians to alert about this conflicting situation. And to finalize, if you realize we have different technologies, but one of those is 5G. This is the commercial 5G that we all have in our smartphones. But for you to know, the 5G is not a standardized, let's say, specification technology for V2X. It is not meant for that. But since all the vehicles, and especially in our pockets, we already have this technology, and the CV2X technology, which is the one that is also be deployed in our project, is not available or not widely deployed in vehicles. I'm going to explain it a bit how we are doing this approach with 5G, which is completely open. Again, there's no specification. But one thing is sure, for that you need a gateway. You need a specific entity placed in the cloud or in the edge, so in the infrastructure side, which has an IP-based implementation, which means that it connects with the vehicles that want to send information or receive information through, let's say, a socket, for example, which is one of the options, but also a publish-subscribe approach. Okay, this, if you want more information, obviously we can provide, but these are two of the main, let's say, approaches that we can follow, and we actually follow both. So two different gateway approaches for the communication with the vehicles through 5G will be implemented to make sure that we have inter-edge, but also cross-border continuity of the services. So if we jump from one edge computing from one MEC to another, the vehicles will find different gateways along the route, and they will be connected or disconnected based on this technologies and approaches, so we can guarantee the continuity of the services regardless the country they are, or the MAC they are, or even the connectivity they have, especially for these use case 3 cross-border scenarios. And this is it.
Thank you so much, Yassine, and also for sticking to the time. And thank you all for your presentations and inputs. I will ask once again for the speakers to open up their cameras, and then we can open the floor to the discussion. I know we are over the time, but I think everyone agrees. Maybe, I hope everyone agrees to take an additional 10 minutes to answer any questions. Any remaining ones, we can also address them offline, but the webinar will be recorded. So if you have any questions, feel free to type them on the Q&A box, and we can take them later, and you can also see them later. So one question for you, Yassine, that was just shared by Luca. Regarding the suggestion of maximum speed in the IVIM message, how do you manage to indicate that it is a suggestion rather than a prescription?
Well, we don't, I would say, for now. There would be a next step, I would say, because there is no specifically field in the IVI for that, if I'm not wrong. So for now, we take all the information that the TMC, the road operator, is generating through this recommendation / mandatory maneuver that the vehicles shall follow, as a mandatory, let's say, content. And we don't deal with recommendations. I would say they are compulsory information that all vehicles shall follow, as the road operator is mandating for that situation.
All right. Thank you. And now a question for Jorge. You mentioned the polygons in your presentation. Could you perhaps give a little bit more details about the definition of polygons you mentioned in the AI model to detect the users by the cameras in the scenario?
Yeah, for sure. Let me share briefly my screen again. You are talking about this image on the left.
Yes.
Well, within these polygons, the road users are automatically detected by artificial intelligence. And well, these polygons are divided into different groups, as many as we need, and we can define two types of polygons: the master ones and the slave polygons. The masters here are the blue ones, and the slave the red ones. Sorry. So if one road user is detected within a master polygon, and another within a slave polygon, in this case, a vehicle in the master and the PRU on the slave polygon of the same, both are on the same group. So the alarm will be triggered as if this symbolizes that there is a possible risk of collision. And well, finally, for a correct, properly operation, the polygons, of course, must be placed in areas where a collision could happen. So we can adapt these polygons depending on the street and the different topology, let's say, of the intersection. And that's all.
Thank you, Jorge. And then I can see another question coming in from our partner, Michael. Is there already a field in MCM for the distance to the preceding vehicle, or did you introduce a new one? I'm not sure who.
Yeah. I can answer that. Yeah,
right,
we are actually using, since the MCM is not a final version, let's say standard, we are actually using an old version that allowed at that moment of the definition to define a distance with vehicle in front maneuver. So the updated versions of the MCM, the latest ones, they don't include it now. but in the previous versions they included it, so we took benefit of that. But we know that if we wanted to, let's say, use the latest possible version of the NCM at this moment, we wouldn't be able to provide that service, and we would need to find another message, or obviously recommend to add this feature again, because it was there initially, to the ETSI consortium.
Thank you, Jacinth. Well, I see no further questions or remarks. So I think since we have come to the end of our plan agenda, we can wrap it up here. Thank you all so much. Let me share my screen also for some last information. So thank you all so much for attending and for the interesting remarks. Before we wrap up, I would like to remind you that we have, you can find some additional information about the PoDIUM Spanish Living Lab in the links that we have in this slide. We will also set the recording, and we will include these links in the follow-up email that we will be sharing. But we also would love to see you at our upcoming webinars. As Jorgos mentioned previously, the next one is next week, focusing on the German Living Lab on Tuesday, same hour. And then in the new year, we will be exploring the Italian one. We hope to see you there. And I would like to thank you all a lot, all the great speakers. And yeah, we will be in touch.
Thank you very much. A pleasure.
Thank you very much. Bye.
Thank you very much.
Thanks, Evie.